Okay, folks, this is lecture number 25, and it has some review, some administrative stuff, and there's an example problem at the end, and let's get to it. So the last three experiments, 12 through 14, I'd like them demoed to me, and I like looking at your Verilog models, your state diagrams, your hardware diagrams. Be prepared to show that to me when you check it off. Okay, additionally, I did some work on the final exam materials. There are some cheat sheets posted out there that you can use in the finals. Take a look at those. There's also a study guide. The study guide is very negotiable. If there's something you think you want on it, by all means, ask me about it. I may agree to put that on there, etc., but you got to say something. So I posted one old exam, which is the spring exam. I actually didn't post the spring of 2018. The spring 2017 is posted. And I didn't post spring 2018 because no one picked it up, and I might reuse some of those problems on there. A lot of the exams before that were just used as different type of material, and it's basically meaningless. I don't even want to post them. I think they were posted before, but I took them down because they're totally useless. So, study guide. Look at the study. Study guide is not negotiable. I'm sorry. The cheat sheets are negotiable. If you need something else on those cheat sheets, let me know and I'll consider that. Wow, that was a big mistake. Okay, onwards. So there, what I want to do is go through these foundation modules real quickly, just a quick overview on these things. In general, digital circuit is a bunch of these modules together transferring information around under the control of something. And what we've been primarily doing is controlling the transfer of information with state machines. Okay, so the state machine, generally speaking, is going to read the status of the circuit and output control signals. So these foundation modules, some of them have control inputs and status outputs. Some of them have data inputs and data outputs. So in particular, this is a ripple carry adder. It has data inputs, has a data output. The inputs are what you're adding. Also has a carry-in, which proves to be pretty useful in some applications. The data out is, of course, a data output, which is the sum of A plus B, typically A plus B plus the carry-in. So generally speaking, A and B are the same width as the sum, which I have listed as an N up there. And there's a status output. The carry out is a status output. It tells me something about the operation that the ripple carry adder is doing. Did it generate a carry out or not? So essentially it's a status signal. Oftentimes we use the carry out as the nth plus 1 bit. So this is the 10-bit ripple carry adder. The carry out is actually the 11th bit, at least for unsigned binary. Okay, next here we have the famous MUX here. Anytime I need to make a decision in a circuit, I am going to use a MUX. Okay, MUXes have a whole bunch of different data in, one piece of data out. The control input on the MUX is going to select which piece of input data is going to appear on the outputs. Generally speaking, all the input and output data matches with input. Generally speaking, all of the data widths of the inputs and outputs match. The control input is a select input. It's going to select which of the data inputs is going to appear on the data output. Comparators, once again, it's comparing these two values, A and B here. Generally speaking, the status it's going to output is either equal, less than, or greater than based on A equals B, A less than B, A greater than B. So once again, this has data inputs, no control inputs. It has status outputs, no data outputs. So generally speaking, you're going to use these in circuits where you need to compare numbers. Generally, it's more complex comparisons. If I want to see, like, oftentimes I can use just gates for more simple comparisons. Generic decoder is essentially a lookup table. I'm going to use that as essentially as in two areas where I have a bunch of computed values I need to output, or as a replacement for complex logic. So we've been primarily using these in the context of output data display. In some instances, we did use them as for logic. I think in the validity checker we use it as logic. So if you use this in your circuit, you have to show me a table that defines it, and after that you're good to go. One form of a generic decoder is a standard decoder. This guy has some select inputs and a fixed output. Now the relationship between the inputs and outputs in quantity at least is there are going to be 2 to the number of select inputs. So if there's 2 select inputs, there's going to be 4 status outputs, such as you see in this circuit. There's always an n 2 to n relationship. So if there's 3 select inputs, there's going to be 8 status outputs, etc., etc. So we use these primarily with the multiplex display. This is going to be, these were used to turn on the correct anode, which in that case we weren't using one hot output, we're actually using a one cold output. Parity generators, we really didn't do that much with it. Generally speaking, you know, you're going to look at a set of bits, and you're going to tell me whether it's has even or odd parity. So that's kind of a parity checker. Parity generator means I'm going to add a bit, typically the parity bit, to the input bits to impose a specific parity on a set of numbers. So if I want even parity, I'm going to add the parity bit to this such that it makes the data in bits plus the parity bit always even. And same with odd. I'm going to add, if I want odd parity, I'm going to add a parity bit such that it makes the data input plus the parity output always odd. Registers. So there's 3 types of registers. There's simple registers, there's counters, and there's shift registers. They're all registers, they're all memory. I'm going to use these in my circuit when I need memory of some sort. If I need simple memory, I'm going to use this register here. If I need something more complex or more feature-driven, I'm certainly going to use a counter or a shift register, and you'll see those come up in a second here. I need control over this thing. These is generally a synchronous device here, so my control inputs, generally speaking, are a clock, a load, and a clear. The load, if I assert the load, it's going to load the data into the register on the next clock edge. This happens to be a rising edge clock. And so this is going to load the data into this register if the load is asserted on the rising clock edge. And once it's loaded, it's going to appear on the data out. Typically speaking, registers have clears when I need them at least. And typically speaking, they're asynchronous. So anytime you're working with a circuit like this, it's pretty obvious what a load does, but it's not clear. It's not clear what the clear does. Sometimes it's synchronous, sometimes it's asynchronous. You need to specify that in your circuit. You know, put a little note next to it, etc., etc. Counter, another type of register. Counters, typically they have the clear and the load. It operates just like a register, but these counters typically can count up or down, or they can hold values also. And typically, you don't really see all these inputs on a counter. You can, all these control inputs, you can use what you want to make your problem work, but typically you have to state exactly how they work. For example, if all I have is an up input, sometimes up, when it's asserted, it counts up, which is fairly obvious, but when it's not asserted, what does it do? Sometimes it counts down, sometimes it holds. So if you have to put that note in your schematic diagram to let the reader know exactly what's going on in this thing. And what else here? It does have a status output. This is RCO, which is ripple carry out. This means it indicates the terminal count. So if it's an up counter, this RCO is going to be asserted when the outputs all ones, all n bits of the output is 1. But typically speaking, if it's an up-down counter, if the RCO is asserted when it's all ones, if it's counting up, it's asserted if it's all zeros, if it's counting down. So the RCO is actually dependent upon whether it's counting up and down for an up-down counter. So typical uses of counters are as an event counter. I'm counting how many times something happened. In that case, essentially, I'm going to tweak this up input every time that something interesting happens, some interesting event, I'm going to increment. Other thing here is these counters, anytime I need to do something a certain amount of times, typically more than twice, I'm going to use a counter. So if I have to do things, 512 times, I'm going to use a 9-bit counter on this thing. If I have to do something twice, I will probably use just states in a state machine. And so what else is interesting about this? Nothing really, but whatever you do, you have to disambiguate your control inputs on this thing. There should be no question of what the inputs are doing. Don't hesitate to put a note in your schematic diagram. Quite frankly, if you don't put a note, it's going to be wrong. So shift registers, generally speaking, they shift. So if I'm shifting right, generally speaking, that's a divide by 2. If I'm shifting left, that is a multiply by 2. So these are really nice anytime I need to do division or multiplication by a power of 2. Shift register is your thing here. So typical same inputs here. I like using this universal shift register, which means it does multiple things. Typically speaking, I like using the select to either load, hold, shift left, or shift right. And so that means this X here would be 2 bits in that case. I don't really go beyond that. So there's another extra data bit here, which is the D bit. This bit becomes the leftmost bit when I'm shifting right. It becomes the rightmost bit when I'm shifting left. Okay, so when you're doing a shift, you're actually losing a piece of data, but you're also adding a piece of data. And the data you add is the D bit. Where you add it is dependent upon the direction. So if you're shifting right, you're gonna shift the D bit becomes the new leftmost bit. Once again, if you're shifting left, the D bit becomes the new rightmost bit. And that's all I can think of on these, and I am ready to do this problem. And this is actually, I think, a good little problem because it does a lot of stuff in here. And I used to think this was an exam grade problem, but it's actually too complicated. There's actually a lot of modules in it, and I don't, as I was saying, if there were 4 questions on the exam, this would be a good question, but it's a little bit too complicated. And so certainly on an exam, I'm not going to make them this complicated, but if you understand this problem, you can understand anything. And like I said, it has some interesting features in this problem. So what I'm going to do here is a circuit that's waiting for a go signal, and what I'm going to do is count the number of input values count the number of times there are 3 consecutive equal input values. That's what I'm trying to say in this thing. And what I'm going to do is monitor 1024 input values. Okay, so I guess the first step in all these circuits is to draw the state diagram. Yeah, like I said, the first thing you do in all these problems is draw that high-level black box diagram. And so I'm gonna draw this thing. Here's my circuit, and it's adding 8-bit values. And let's put a thou. It's not adding them. It's looking at them. Okay, so there's your 8-bit values. By all means, this has a clock. And what else do I have in this thing? It looks like a go button on this thing, and it has an output. I'll call it count. And is that all I need on this thing? Yes, that's all I need. I'll call that done. Okay, so it's not actually done because I need to establish the width of the output. And so what it's looking for is three, anytime there's three consecutive input values that are the same, that's what I'm going to count. And so I'm going to check 1024 values. And so the notion is, if the count could be 1024, I would need 11 bits on this thing, because with 10 bits, I can only count up to 1023. So 10 1 bits, 10 bits that are all 1 is 1023. This, in a circuit that could be 1024, I would need 11 bits, but this isn't going to be the case in this thing. So it makes sense that worst case, I'm looking at 1024 things. It's not going to be 1024. It's actually going to be 1024 minus 2, which is less than 1024. And I don't really care exactly what it is, but I know that it fits into 10 bits. It's not going to be greater than 1023. I think it's going to be 1022 maximum. And so that looks good. Okay, so the next thing in this problem is to discern that, hey, I'm going to for sure be comparing three things. And so it'd be nice to say I have a 3-input comparator, but I don't have a 3-input comparator. So the very first thing I'm going to do in this problem is design a 3-input comparator. And so this 3-input comparator is actually going to be two 2-input comparators. And this is actually like a week 3 problem. And so we'll call this A and B and C. And it's going to compare these things. We'll call it 8 bits because it's an 8-bit problem. I'm sorry, I'm probably like fading out there. Okay, so anyway, what I'm interested in is when these three are equal, both these equal are going to be turned on, which means it's an AND gate sitting there. So hopefully that's not a big deal for you guys. Hopefully that will be like a week 3. If you recall from week 3, I know we did stuff like that. Okay, so that's my 3-input circuit, and I'm going to go ahead and use that somewhere in this diagram. I'm not quite sure yet where. I'll put it in when I need it. So the next part of this diagram is I've got two things going on here. And so one of them is event counter. I'm counting an event, and the event I'm counting is when those 3 inputs are equal. So I know I need a counter. It's kind of the centerpiece of this problem. We agree that it's 10 bits, and there's my count on this thing. It's a clocked circuit, which is good, and I certainly need to control when I count up on this thing. It's a counter. It's essentially working as an event counter. I'm counting events. So by all means, I need to be able to clear this thing initially. Okay, and a load. I don't think I'm loading anything, so I can get by without sticking a load on that thing. And I think that's good. So that's my event counter. And so the other thing I need to keep track of here is I'm going to monitor 1024 inputs. So certainly I could make a state machine with 1024 states. I don't want to do that. Essentially, I want a second counter here. That is a 10-bit counter that I'm interested in the RCO. I also want to make sure he starts at 0 so I can clear the thing. And I think it's always counting up, and so I don't think I need to worry about the up input as a control. So I can put up and clear also make it self-consistent. Okay, so the neat thing about these two counters is one is used as an event counter, which is the top one because I'm using it as I have control of the up input. The bottom one is just used to count how many times to make sure I do something X amount of time. In this case, because it's 10-bit, it's going to do something 1024 times. What I'm interested in this thing is a replicate out on this. So anyway, it's looking good on this problem. I'm going to
I know this needs a state machine, so I'm gonna come over here and draw the state machine. And I've got two control inputs sitting there. I've got a clear and I got an up. By all means, it's clocked. I know I have a go button that's going to feed into this thing. And I have an RCO that's going to feed into this thing. And do I need anything else? God, I can't think of anything. I'm just going to... Oh, yeah, I certainly need something else, and that's the next thing in this is a comparator. And this is my comp 3 device that I previously designed here, and it's going to have 3 inputs, and we can worry about those inputs in a second here. And I'm almost ready to go on this problem. There's one more trick on it, and that's handling the inputs. Okay, so I need to compare 3 things. I only get one of those things at a time, so I'm hoping that it makes sense that I'm only get one fresh thing. I got 2 old things. When I mean 2 old things, that means I need to save 2 old values so I can compare them. So anytime I need to save information, it's going to be a register. There are my 2 registers. These are 2 of the things I'm comparing, and looking good on this thing. And the other thing I'm comparing, what I'm comparing it to is the in-val. So this is val, and all these are 8. Looking good. Okay, so the comparator's hooked up. What I need to do is get these registers hooked up properly. Okay, so what I need, and they're clock devices, so I can put the clock on them. And I'm not going to worry about the load until maybe, I don't think I need a load on these things, but I'll figure it out in a second. So what's going to happen every clock cycle? It's going to compare the current input to the oldest input, and also to the second oldest input. So that means the second oldest input is going to be one stage older than the, oops, I didn't want to do that. One stage older than the first input, the first old input. Okay, so the first input is going to be loaded with, I'll put some data on these things. First input is going to be loaded with that input value. Okay, and I think I'm done on this thing. So it's comparing the input value to the previous value to the really previous value. And these are all 8 bits. And I think I'm done and ready to go on this. Loads. I don't think I need to worry about the loads, except I don't need control over them. It's always going to be loading. I don't need to clear these things because I'm always loading new values into it. And I think I'm ready to go. I think that's all the hardware I need, except for the fact that I have an EQ sitting here. EQ is a status input, and it's going to be an input to my state machine. So I got the hardware set up. The very first thing I need to do before I start counting events, I need to get these registers loaded. So it's going to take 2 clock cycles to load those registers. So I don't have any real cool way to do it. So I'm just gonna plop down some states to do that for me. Okay, so we're ready to do the state diagram on this. Okay, this is my wait state. It's waiting for a go signal. I'm going to say LD1. Okay, here's my go. I'm going to put this down here as go not, clear not. So I get a go, I'm going to clear. I want the output persistent, so I'm going to, what am I going to do on this thing? Turn the up input off. So this is the up input. I want it persistent in the wait state, so I'm just going to make sure it's not counting. Okay, so it looks good. So I need to put 2 notes on this thing. So say up, equals 1, increments. You know what? I'm not going to put that there. Put it somewhere else. I'll say up. Up equals 1, increments, up equals 0. It holds. That covers this counter, and I'm also going to say clear is asynchronous. And that makes this clear work right here. Okay, so that's a clear, and that's not a clock. I'm going to better fix that. CLR. Okay. With the overbar over it. Okay, looking good. Now, if I didn't put this information here, it would technically not be right. You could guess it would be what it was doing, but you don't want to guess. Okay, so the first thing I want to do in this thing is load those registers. So it's going to load automatically after it gets cleared, because I got these loads tied to high. Okay, so after this first state, it's going to be loading the first register here. What I need to do is keep the clear off and make sure I don't count up on this thing. And so I'm going to do that again, because I got to get that second register loaded. I'm going to keep the clear off, and I'll keep the up off. Okay, so this is unconditional transfer, and by the time I exit the state, I'm ready to count. Okay, so in this state, by all means, I'm counting. I certainly don't want to clear. And these are both unconditional transfers. I need to indicate that. So two things are going to happen here. One is I got to worry about, I got the clear input handled. I have to know what to do with the up. So the key to this thing is, I don't know how to say it. When am I going to count? So I'm going to count when this equal is asserted. So what I'm going to do is assign up to equals. That's going to be my event counter. The event I'm counting is when all three are equal, which is what the circuit gives me on this thing. And essentially, I think I'm done. And as far as the output goes to that state, what I'm interested in here is transitions. So RCO. If I'm not done, blah blah blah. Once I am done, I transition back to the start through the wait state, where I'm actually holding the input on that. And I think I'm done with this problem. Interesting thing here is this 3-bit comparator module. I defined it elsewhere, and I used it in my circuit. All the transitions are accounted for, particularly even the unconditional transfers. I put a dash there. If it was just an arrow without the dash, it would not be correct. And typically speaking, I mean, this clear here, the way I've used it, I've designed it as a Mealy machine. It looks like a more output in these states, and essentially is acting like a more output in these states, but it's really truly a Mealy input, because in this wait state, the condition of the clear is based on the go. So in this single state here, wait, sometimes the clear is asserted, sometimes the clear is not asserted. And so up here, if you look at up, it's truly a more output. Yeah, so more is now. I mean, I got it stuck in every state. Kind of interesting version right here, but it's truly a more output. And so once again, really great problem. If you understand this, you can do anything. I thought I wanted to put this on the exam, but I think it's a little bit too hard, in that there's 1, 2, 3, 4, 5, 6 modules. This one module is made up of 2 modules. There's like 7 or 8 modules on this. Great problem. Too hard for an exam with that many problems, and I intend to put simpler problems, less hardware, maybe the same amount of states, but less hardware. And folks, that is all I have for this problem. Make sure, like I said, anytime you're using counters, you have to disambiguate the inputs. I probably should also say clear has precedence over the up, but I'm not gonna. If you don't put that in an exam, that's fine. Everyone assumes that to be the case. Anyway, good luck. Ask me questions if you got them.